All right. We're all set, Professor.
Okay. So hello again. I'm not quite sure what's the best way to give this talk. I think it's probably more like a discussion with you guys. And so if you have questions you always wondered about that's related, I will be very happy to answer, and feel free to just stop me and ask questions. I have put in a lot of things that we have been working on in my group, but there's not really a need to go into details of every one of them. And more, I think it will be more fun if you could find some answers to some of the questions or find something more interesting and we can discuss about it. So, but generally speaking, what we work on is basically looking at the light-matter interactions and using light to control matter, and sometimes vice versa, to look for new phenomena and hope it may also provide a base for future new technology. So why matter-light interactions? That's actually at the foundation of modern science that starts from where we realized quantum mechanics is at play in nature. Let me turn that laser pointer. Right, from the absorption spectrum of sunlight till where we see a shift of the energy levels due to vacuum fluctuations of electrical magnetic modes that leads to the Lamb shift. And when we can harness and can understand this and harness this power, we can create a technology like lasers, which is used everywhere now, from communication to medical science, of course, to scientific labs and to industrial factories. And we can use laser in turn then to control the matter again, such as trapping atoms, even single atoms or cool atoms to create condensates, and doing similar things on the solid platform as well. And of course, it's light-matter interactions underlies a lot of the modern technology as well, such as the displays, laser pointers, and there's a lot of interest in photonic computing, both classical computing and quantum computing. So what we're interested in doing, the specific systems we work on more recently are basically two types of sort of a link between two topics. The first one is to look at where the light-matter interaction becomes non-perturbative, or we cannot treat it as a perturbation to the matter, but light becomes part of the eigenmodes of the system. So that's what we call, when we say we have a strong coupling regime. And in that regime, the eigenmodes of the system has to be described as a hybrid of matter and light. If you have done second quantization, so that's typically how we like to describe quantum mechanical modes. So that's an annihilation or creation operator of the photon, quantized photon mode. And that is the one for an exciton, or basically the lowest energy electronic excitation in the semiconductor. And when they couple strongly, you can diagonalize the Hamiltonian, and what you get, the new eigenmode, is just like in coupled harmonic oscillators, you get a linear superposition of these two quantized modes that gives you the new quantized mode, or what we call the Polaritons. So that's a system that we work a lot with. We used to work a lot with it using more conventional materials, which are, the materials are very mature. We basically use it to build a platform to study new physics phenomena, like to create those Polariton modes and see what interesting things can happen once we have such Polariton modes. So what's good about them? They are literally hybrid, half light and half matter, right? So the light part gives us basically robust coherence, because that's what light is the best at. It doesn't interfere or doesn't interact with anything. It keeps its coherence if you don't disturb it, if you don't interact it with the matter when it is left alone. So, and it also has a long length scale, which is wavelength length scale. So that sort of imposes a relatively long range coherence into our matter system and make our matter system insensitive to electronic disorders that's on the nanometer scale or much, much smaller scale than the wavelengths. And at the same time, the matter part brings into our light system interactions or strong nonlinearity. So if you can combine the good part of both, then you get to have access to a lot of interesting things that you can't access in pure matter or pure light systems. So for example, there are many interesting phenomena that can, many body phenomena that can emerge in this system as a sort of analog of ultra-cold atomic gas, except that it's on the semiconductor chip, and it can operate at a much, much higher temperature than cold atomic gases. But it could have very similar type of physics with its own characters. And since it is already on the chip, it also sort of provides a very natural bridge to potential technology. And there are many concepts of using such a system for basically energy efficient nonlinear photonic devices. So the other type of system, so now switching over, another topic we have worked a lot on lately is different materials. And I guess a lot of people are very excited in recent years with the emergence of those two-dimensional van der Waals materials. It was the first best known one is probably graphene, which was already given a Nobel Prize for. But after that, people have discovered graphene is not unique in terms of how you can make it into a single molecular sheet. There's a larger group of materials called van der Waals materials all can sort of make into single sheets. The reason is because the reason they are called van der Waals materials is because they basically form covalent bonding between atoms or molecules inside each layer. But between the different layers, there's no dangling bonds. So they only have they are like perfect crystals with no hanging out electrons. So they can only bond through the van der Waals force. So that's a very, very weak force compared to the Coulomb force bonding or other type or ionic force that's bonding for the implant bonding. And that's the reason you can peel off these materials layer by layer quite easily with a Scotch tape or with various types of polymers. And because there doesn't have those outer plane dangling bonds, they are stable, even just as a single molecular layer. And they are much, much less sensitive to the surroundings compared to conventional materials. So the surface effect is almost diminished compared to conventional materials. So that's what makes them so special, both for graphene and later on for a larger group of compounds that are also this type of van der Waals materials. And they are also extremely interesting for optics or for light matter interactions, because when we go to those two-dimension, reduced dimensionality, like shown sort of here, if we have a bulk, if we have a multiple layers, then the Coulomb interaction between an electron and hole, or between two electrons in the material will fill the rest of the lattice and the electrons in the solid. And the rest of the solid will sort of reform itself a little bit to reduce that interaction. And that's called the screening effect. So, and that can be estimated with a dielectric constant. Right? So Coulomb interaction is basically reduced by dielectric constant to some power. So it is reduced by a few orders of magnitude compared to in free space. However, in such material, as you can see here, since it's only a single molecular layer thick, the Coulomb interaction field lines actually mostly go outside the plane and don't see the screening. This is sort of very cartoonish hand-waving way to see why the Coulomb interaction becomes much stronger in the 2D materials. But that is one of the very important features. So when Coulomb interaction is strong, the electron and the hole gets a strong binding. Then the exciton and polariton physics that we study becomes much more pronounced or much more robust. So with the conventional materials, we do all of this at a liquid helium temperature. But in those van der Waals materials, they survive at room temperature. So you have never heard about excitons when you use your electronic devices or you use your LEDs, because the excitons dissociate. They don't have enough binding energy to survive at higher temperatures. But in those materials, they will be the dominant excitation, or they will dominate the physics that's happening in these materials if we ever use them to make devices. So they have a bunch of other very unique properties as well. And another extremely nice thing about this material is that they can be peeled off with the Scotch tape. Right? So you buy a commercial crystal, you go to the lab, then you just need to work hard to make the best crystal possible in the world, rather than spending multiple $1 million and many decades to do the fabrication that's required for conventional materials. So that makes them extremely versatile. And now you can also combine multiple layers to just make heterostructures. So we're still studying a lot with the Polaritons, just on conventional materials, because that's such a mature system that has a lot of interesting physics to explore. While at the same time, we're also looking at many properties of those two-dimensional materials for exciton-polariton physics. So I think I will mention both topics. The first part is the more polariton physics in conventional materials, and the second part is about what happens in those 2D materials. So any questions about this somewhat general introduction? Okay, I hope they all make sense. So let me just go quickly what exactly is Polaritons. And as I mentioned, what we're interested in is basically light matter coupled system. Right? When you have a semiconductor, when you go to sufficiently low temperature or low energy scale, the lowest electronic excitation is you take an electron from the field valence band to the empty conduction band and leave a hole in the valence band. But they will have a Coulomb interaction, so they can bond to form an exciton. So that's the excitation we have. It's an electron hole pair. And it has a dipole moment, which means that it can couple to light. So you can create such an excitation by shining light on it and transfer the energy from the light into that excitation. So, but when you typically when you do that, that excitation will go away because the excitation is not a ground state, right? It could go away non-radiatively, or it could go away by emitting another photon. But typically, when you have a lot of inhomogeneity and the decoherence, etc., those events are all separate. You can treat them independently, meaning they don't know about the phase and coherence from the previous event until you have very strong interaction. So the absorption and emission and even reabsorption and re-emission becomes shorter than any decoherence. Then in the quantum mechanical picture, you no longer know if you have photon or if you have exciton. they are there in your system at the same time. They're not distinguishable anymore. So that's when you go to the strong coupling region and get these new eigenmodes or this hybrid exciton and photon modes. That's what we call the Polaritons. And when the hybridization happens, that at the same time you get the level splitting, energy level splitting, and the separation between the levels will basically corresponds to the interaction strength. So in conventional materials, how do you get it? You want the interaction to be strong enough. And typically that means we need to confine the photon strongly using cavity, which is basically two high reflectance mirrors. So the photon will bounce back and forth. You get the length exact, half lambda, for example. So the photon will have antinodes, or the cavity field will have antinodes where you can put the quantum wells and enhance the interaction between the exciton and the photon. And then we can get to the strong coupling region. Then we have our Polariton modes, and we have the nice things from both the exciton world and the photon world. So the exciton is an electron hole pair. It has electron and a hole, so it adds up to integer spin as well as a photon. So these polaritons behave more or less like bosons, but they are not true bosons. They are composite bosons, so they do have interaction, or they are weakly interacting bosons. And people have done a lot with those systems to look at, for example, oscillations, and there are a lot of very interesting theoretical proposals as well to create arrays of such structures to build a simulator, Hamiltonian simulator, which could be a classical Hamiltonian or a quantum Hamiltonian, and to build matter wave devices, or that both have a long-range coherent transport and strong interaction for information processing. Along those lines, one of the things we focused on was basically to see how we can better control those Polariton modes. So typically, we have to bury the quantum wells inside a cavity, and we have to make everything perfect to reduce the dissipation, the decoherence, etc., to really go to the coherent limit, right? So the cavity is grown by molecular beam epitaxial in the monolithic structure, and the mirrors are made by a huge stack of alternating half lambda pairs, which we call the distributed Bragg reflectors. So that makes it sort of difficult to control the properties of these modes. So what we do is to remove such the stack and replace it with a photonic crystal grating. And with a photonic crystal, and the simplest type is just a grating. So instead of a vertical feedback, we utilize the horizontal feedback to form a mirror. And if you're interested, I explain why it works well, but it works well and it could even work better than the conventional types. But what the photonic crystal gives us is basically many parameters now we can control and vary, and to adjust the properties of the photon mode. Now that since we're in the strong coupling region, photon is just a part of the polariton. When we do something to the photon mode, it automatically transcribes to the polariton modes. So that's give us a huge flexibility to modify the properties of the quasi-particles we work with. So I'll just sort of flash through some of the things we could do with such a system, and or some of the properties we study. Here is an example that when we create such a system, we can simply, so here I sort of imply we have an infinite system in the XY direction. In the Z direction, we have confined photon mode and a quantum well that confines the excitons. But in the XY, it's infinite. And that's typically the case for the DBR cavities. And it's very involved in order to reduce the dimensionality. But with these gratings, we can just make the gratings as small as we want, as long as there are still maybe 10 periods or something. And then effectively impose a transverse confinement. So that's what's happened here. When we just reduce the grating size to about a few microns, we get a fully discretized photon modes. And that gives us a fully discretized Polariton modes. And what discretization does is it suppresses quantum depletion or thermal depletion between the different levels. And it also suppresses mode competition when you want to form a single coherent many-body state. And so when we do that, how do we know we have a nice single many-body coherent many-body state there? So that's characterized by what we call the coherence functions. There are first order, second order, third order, and so on. So for coherent state, like in the laser, it's defined as all the coherence functions equal to 1. And if you have a thermal state, then they will differ. To get the statistical properties of the state, the lowest order you need to look at, or the most important order, is the second order coherence. And for coherent state, it should be a Poisson statistics. And for the thermal state, you would have a 2 or something that's called a bunching. And for a single photon state, you would have anti-bunching or below 1 that gives a quantum state statistics. So with such a discrete states, we were able to reach the Poisson limit to confirm it is indeed a nearly perfect coherent state statistics-wise. And we can also check its phase coherence. This is somewhat more involved, but basically we could see that in the limit, we don't have a lot of polaritons in our laser. We follows the typical lasing behavior of a photon laser, which has what we call the shallow toneless line width. That line width keeps decreasing, or your coherence keeps increasing if you have more and more particles in that same mode. And that's because of the boson final state stimulation from the boson statistics. And however, we do have a matter wave laser that has interactions between those composite bosons. So if we put enough number of them into our laser or into our condensate, the interactions will start to show up. And that's what gets us into that regime. And that reflects in the change of the phase coherence function, both its value and its shape. So we can use the system to study the details of the coherence properties of the many-body state we form. Another interesting regime to look at is what if you get enough number of excitations, you deviate significantly from this weakly interacting boson picture. Shown here is basically the electron occupation number versus the wave number. So if you have very low occupation, we basically has almost like a classical gas or Maxwellian gas, and we need to worry about its Boser or Fermi statistics in the electron hole picture. And that's where we can get the excitons to behave as bosons and create both Einstein condensate and create Polariton lasers. Electrons, eventually the electrons will know it is fermions when it is started to feel the effect of each other, because we know we can never put more than 1 electrons into the same state for fermions. So the wave function of your exciton, or the distribution function of the electron, will be changed from like an exponential Maxwellian to a step function at a very high density limit for a fermion system. So what happens when you go through that transition? It turns out we can have a combined formula to describe this transition from the low density limit to the high density limit, which turns out to be a wave function, has the same form as people use to describe conventional superconductors or the Bording-Cooper-Schrieffer states for superconductors, where you have Cooper pairs. There, in the superconductor, you have electron-electron forming a Cooper pair. But here you have the electron and the hole forming a Cooper pair in quotation. But the physics is the underlying physics, or the formula to describe them, actually turns out to be very much the same. And that is what called the BC to BCA's crossover. Here is the BC limit, and here is the BCA's limit. So this has been postulated since the 1950s, and it has been seen in atomic systems in the early 2000s. That was a huge deal for atomic physics, because that's basically a milestone. They can really control the system and tune the interaction between these two limits through what they called the Feshbach resonance. But in semiconductor systems, although the prediction has way predated atomic systems, it has been very difficult to see, because once you go to those high densities, decoherence, dissipation, all of this will increase, and that kills the coherence. And all this picture we have been describing here are theoretically worked out in the thermodynamic limit of zero temperature and the infinite number of particles, etc. That just doesn't work for real experiment. And so for the Polaritons, a similar crossover should also happen, except in addition to electron and hole, now we also have a photon that couples strongly to this electron and hole pair. And there are predictions that such coupling should actually, again, enforce the long-range coherence and enforce the pairing between the electron hole, even in the high density limit. And there have been various studies, but the experimental signature is difficult to obtain, because this is called a crossover, which means it's not a phase transition, which means you may not expect an abrupt change in any of the thermodynamic properties or statistical properties you could measure. So that makes it very hard to detect and confirm such a crossover experimentally. And the typical ways we look at this system is basically through the emission of the light. I'll skip that, but if we just look at the emission of the light, we have learned how to distinguish between a polariton system and a photon laser, where the polariton dissociate. But to distinguish between the BEC and the BCAs, the fundamental difference exists in the electronic system and cannot really show up easily in the photon emission itself. So that's another way we can use such a grating cavity. And what it does is that the grating apparently breaks any in-plane symmetry, right? So that now we have two linearly polarized modes, depending on the direction of the grating bars. And one of them can be designed as a high reflectance mirror, while the other one will not be. So for one polarization, we have our strong coupling and the Polariton modes, as shown here. And for the other polarization, we don't have a strong exciton and photon coupling. So we just have electron hole, essentially just a classical electron hole plasma. That's shown here. And the energy difference between here and here is basically the level splitting due to the coupling in the cartoon before. The nice thing about it is that both of this do share the same electronic reservoir. So now we can look at this one to see what happens for the polaritons, and look at this one to see what is going on in the electronic reservoir that was difficult to access before. So our basic finding is that if you just look at this one alone, you will see a lasing that's indistinguishable between a BC limit and the BCA's limit. If you look at the TM mode, then you will be able to see whether or not there is gain in the electronic system. So the key thing about the Polariton BEC or Polariton lasing in the BEC limit is that it forms because of the Bose-Einstein condensate, right? Because bosons want to go into the same state. And that's how you form the condensate. So that's the thermodynamic ground state of the system. And what that means is that if you work out the thermodynamics right, that's basically the state the system wants to go into. That's the lowest energy state. And that's very different from a conventional photon laser or semiconductor laser, like we typically use in our laser pointers or in our lab. And in those systems, what they require is what we call the population inversion. Means you can absorb a photon, but you can also emit a photon. So you want the probability to emit a photon to be greater than the probability to absorb it. That's where the stimulated emission or amplification comes from, the A in the laser. But that population, that requires you have a more population in the upper state than in the lower state. That's how you can have more emission than absorption. And that's called population inversion. And there is the equivalent thing for semiconductor laser or population inversion density. That sets a fundamental bound for the threshold power you need for a semiconductor laser. But for Polaritons, we don't have such a requirement in the BC limit because that's the ground state of the system instead of the inverted state. However, in the BCA's limit, that's basically where that picture breaks down. We don't have these bosons, and we don't have the stimulus scattering into the excitonic modes anymore. So we actually do require population inversion or gain in order to form the macroscopic coherence or the lasing state. So that's basically what we could find out when we look at the TM mode. So combining these two, we could actually identify if the system is in the BC limit or in the BCA's limit. And we can verify that with theoretical predictions of the various properties as well. So that's with one of those cavities. Now, if we actually couple two of them, what happens? If we couple two superconductors, for example, the well-known phenomenon is called Josephson oscillation, or you can think of basically the coupling will split it into the binding state and the anti-binding state with different energies. Right? And we can probe that physics quite easily with such a basically a photonic crystal grating type of mirror. And we hang those mirror above an air gap with those tethering structures around it. And there will be strain when we remove the underlying layer. So this grating will be buckled, and that will translate to different cavity length. And that will translate to different cavity energy. And that will translate to different polariton energy. And that gives us effective potential for the polariton mode. So just by doing that, we can actually create, in this case, a double well potential for our polariton particles. And you could see here, it has now the bonding mode, the symmetric mode for the ground state, the anti-symmetric mode or the anti-bonding mode for the first excited state, which is dark in the middle, which also maps out very nicely into the Fourier space wave function. So if we look carefully at these two lowest states, the bonding mode and anti-bonding modes, and look at how they change with power, below threshold, fine, they're just some thermal state, right? When we go to high enough excitation density or very high excitation density, we see lasing in the lowest mode, the bonding states, because that's the lowest state. So what caught us by surprise is that in the middle, we see there are many new states appeared. That's not the original A or B states, but a number of other things appeared in the middle. And it turns out, how do you get new states or new frequencies, right? There are new oscillations. And in this case, what gives that is what we call the limit cycle. All the systems simultaneously start to oscillate at a frequency that has nothing to do with original energy or the cavity property. it comes just from the nonlinear dynamics of the system itself. And it turns out to be one of the most famous and difficult mathematical problems in nonlinear dynamics, and that underpins many phenomena like our beating of our hearts, why it beats rhythmically with a certain periodicity, and how the firing of the nerve cells and our circadian rhythm, or why we get jet lag and these type of things. So it turns out to be a very intriguing fundamental question in math and in nonlinear dynamics, and which can be explored in our quite simple coupled cavity system. So the intuitive way to see what leading that to different from simple Josephson coupling is that we not only have a coherent coupling between them, but also in such a cavity system, we have dissipation or get an imaginary part in our coupling. And in that, so we get a complex coupling instead of a pure imaginary coupling. And in that case, you can solve the equations and show that such a rich nonlinear dynamic phenomena can take place. And we can also verify it by, again, checking the phase coherence properties, et cetera, et cetera. And we can map out the phase diagram, how it changes from stabilizing to limit cycle, which is also a precursor to chaos, and so on. So I think that's that part. And there's some other fun things we could play with using the system, such as building. If we create our grating in such a way, what we get turns out to be a vector beam, where what's shown here is the polarization of the beam begin to rotate around the center. And that beam is called a vector beam, and it can be described by two counter-rotating vortices. And that's why the center is completely dark, because that's the center of a quantized vortex. And we can also change the dispersion. I think I'll skip this part and make a logic arrays of the system to basically build a simulator and look at all kinds of different physics. And there are many theoretical proposals to study various phenomena in such systems as well. I think with that, I will move on to the second part, or on the 2D materials. Any questions for the Polariton stuff before I move on? No, okay. So as I mentioned before, some of the two of the most important, I guess, attractions for us to study those 2D materials is because the reduced Coulomb screening, the very strong exciton and the Polariton, very pronounced exciton-polariton physics in this system, and also the fabrication flexibility. It gives us a playground, literally just the possibility just limited by your imagination and your patience to make those devices. So how strong is the exciton-polaritons and how robust are they? And here is the example. So with these traditional materials, as I mentioned, we have to use typically MBEs, molecular beam epitaxy, to grow the materials one layer by one layer into a few micron structure, monolithic structure, in order to build a high quality cavity. And such a growth takes $1 million machines, and also many hours, typically 10 to 20 hours for a single growth. With these 2D materials, however, we don't need to care about what materials we have to integrate them with anymore, because they are rather insensitive to the environment, to the substrate. So we can just take some of the most commonly used material that's cheap to make and easy to make with very well developed recipes, go to the clean room. For example, in this case, make a grating out of silicon nitride on top of a silicon dioxide, and simply just stamp that material on top. It's just a single monolayer So even though it's outside this grating and the field becomes evanescent outside the grating, that's still strong enough right at the surface. And we can easily get to very strong coupling between the material, between the photonic structure and the material. That's shown here. That's shown here. And also we can easily vary the grating parameters to vary the wavelengths and cover a wide range of materials. And when we do that, we actually also right away get into the strong coupling regime, which is shown here, where the cavity mode now split into two with the anti-crossing there, gives us the upper and the lower polaritons. And that even happens at a room temperature instead of the liquid helium temperature we have to work with for materials like gallium arsenide. And we can push our log further, even remove the cavity. So what that means is that we no longer have this very strong field enhancement from the cavity. How does the cavity, how well does the cavity confine the field, right? If you think about two mirrors, let's say the reflectance is 99%. So we actually typically need to use mirrors with a reflectance of 99.99 or higher in order to form those gallium arsenide polariton cavities. But if you take it as 99%, that means when the photon bounces over, it has a 99% chance of going back and only 1% chance of escaping. So it takes it 100 bounces in order to escape. So the field, which means the exciton can interact it 100 times instead of one time. So hand wavingly, you basically get 100-fold enhancement for your coupling. Right. So a high reflective mirror makes a huge difference for the coupling between the light and your materials. However, if you take that away, then you're basically at the vacuum level. It's a single pass. If you put one mirror behind, it's a double pass. Right? So in conventional materials, that means there's no way you can get to a strong coupling regime with a thin layer of materials. And when you do that, which is also typically what you deal with materials when you don't put them into a high quality cavity, what you will see when you send a light to it and look at the reflection or transmission is that you will see some absorption. And the absorption will be very tiny, typically less than a few percent. And it has a certain height and width. The area underneath is conserved. That's called the optical sum rule, depending on how many dipole oscillators you have in your material. So the taller, so the narrower the broadening, which is typically inhomogeneous broadening, the shorter the absorption peak. The narrower the broadening, the taller the peak, but the area is conserved. That's also called the Beer's law for optical absorption. But what if in our system, the light and the matter interact so strongly, it always stays in the coherent limit? What do you think should happen to the absorption? What that means is that now you basically, if we imagine we can remove any dissipation in the decoherence, so the line width should get narrower and narrower, and at a certain point, it will reach 100%, it cannot go over. When you keep going even narrower in line width, the peak cannot increase anymore. It can stay there, or it can decrease. In either way, the area will have to decrease. Means the absorption will have to decrease when your material actually interact with the light more strongly. And if you work it out, it turns out if you are completely coherent limit, if you can neglect any scattering or dissipation, you will never have any absorption. Your material, even just a single layer of material, will function as a perfect mirror. Does that make sense? So it turns out what happens is that if you don't have dissipation, you can, so what it really means is that absorption is necessarily defined as an incoherent phenomenon. When you don't have dissipation, whatever is absorbed will be re-emitted coherently. Going coherently means going back to the same field. And that's why when you don't have any dissipation, absorption actually disappears. So we don't go to exactly that limit. We don't really have a 100% reflectance from a single molecular layer yet, but we could already see very clearly the effect of it, of going to the coherent limit or going to the limit where such a coherent interaction dominates over incoherent dissipation. And that's where we could see, simply by changing the distance, for example, we could see the modulation of the line width, and that also corresponds to a shift of the resonance, which has an analogy to the Lamb shift, which is the original Lamb shift is a pure quantum mechanical phenomena from vacuum fluctuation. In this case, it's called a collective Lamb shift. The physics is similar, but it's in many body systems and have a semi-classical description. Now we still have an interesting point in the middle where the absorption goes to 100%. And 100% means it's complete absorption, or what we call perfect absorption. And turns out that condition is reached when we have the scattering rate or dissipation rate equals the radiative decay rate. So the radiative decay rate is basically the measure of the strength of the exciton and the photon coupling. And we could see if we can get there by changing this condition, which we can change by change either the dissipation or the coupling. Changing the distance between the material and the mirror, for example, has a small modulation of the standing wave field strength that changes this parameter. If we change the power or the temperature, we can change this parameter. And that's what's shown here, that it goes through a maximum in all these cases. And in the best case, which is changing the density, the excitation density, we get a maximum of 99.6%, or we have a 99.6% absorption by a single molecular layer of less than a nanometer thick. So that's sort of a quite a remarkable how such a property of such 2D materials, that you can just tune the mirror behind it to turn it into a perfect reflector to a perfect absorber. So now going back to my favorite equation of 1 + 1. So in this case, since we have the flexibility to just peel off and stack those 2D materials, 1 + 1 is also one of the most interesting prospects we can do with those materials. Just to stack 2 of them together and see what happens. It turns out that there's extremely rich realm of physics you can explore, as well as potential applications. So let me go through some of them. Here's just an example to show that it's really a handcrafted device. You can see how irregular each of the layers are. And we stack them, take pictures, and carefully label them what they are. And we have ways to determine how the different layers, the crystals, are oriented with each other. I think I will skip this one. I would say maybe I should mention this briefly. So this is one combination of such a bilayer. In this case, is tungsten dicellulide and molybdenum dicellulide. So why do we want to put different layers together? As you see, they have different band gaps, and the conduction and valence band will line up differently. So for this particular combination, the band gap is lined up in such a way, which we call the type 2 band alignment. So the electrons will have the lowest energy in this layer, while the hole will have the lowest energy in that layer. So this interlayer exciton becomes the lowest energy state. And it turns out, since these two layers are only less than a nanometer apart, it is very fast for the electron to go from one to the other. So we can pump, create excitation in this way. And then this one will go here very quickly, on the order of less than a few hundred femtoseconds. And then they will combine into this state. And this band was initially empty. So it's very easy to build up a population inversion. And that leads to a lasing threshold. And that's what we did in this experiment, where we can see a clear lasing threshold. And we can also measure the spatial coherence to show how the lasing state has formed. But an even more interesting thing about those materials is that they can actually form what we call Moire lattices. Let me just show this first before I go there. So these are some of the commonly used 2D materials, and you could see how their band gap line up. The one I showed before have what we call the type 2 band alignment. But these two pairs, if we pick these two materials instead, their valence band are misaligned, but the conduction bands are quite close to each other. So when you do that, what happens is that now the electron has a very good chance to jump back and forth between the two layers instead of going into one and stay put there. And such a tunneling, what such a tunneling does, you can describe in different ways. One way to describe it is when it is here, it forms an exciton, which we call the intralayer exciton. When it jumps back here, it forms a different type of exciton, or the interlayer exciton, between the electron here and the hole here. And these two states have a very different coupling strength with light. Here they are in the same layer, they couple to light very strongly. Here they are in different layers, they couple to light very weakly. So if we measure the absorption, we can tell if we see nothing, we probably have such a transition. If we see strong absorption, we have such a transition. So that gives us a way to know what is happening in the system. So here is an example where we can see the many resonances of those intralayer transitions in one monolayer and in another monolayer. But when we stack them together, every one of those resonances split into two because they become hybridized. Every of these intralayer transition become hybridized with the interlayer transition. Once they hybridize because of electron tunneling, they share the coupling strengths from that transition. So the absorption strengths from this one now get split into these two coupled resonances. That's how we can see these coupled resonances. And that also gives us a way to know we have such coupling, a hybridization going on in the system. And we can use that to deduce the tunneling strengths, et cetera, et cetera. Right? Now, if we twist these two layers relative to each other, change their crystal orientation, then the band bottom of the two layers will become displaced. So once you have this, then the momentum conservation will forbid hybridization between these two states. But interestingly, we could still see those split peaks. So it turns out what happens is that what's forming the system is called a Moire lattice. I'm sorry, I should have included a picture of the Moire lattice. Let me see here. At least I can show this one. So here is the example. If you put these two layers together and twist them, you could see a larger pattern that's getting formed. And that's the Moire lattice pattern. Now the period of such a Moire lattice becomes much, much larger than the underlying period of the crystal lattice itself. Okay. So In the Fourier space, what that does is band folding. If you have taken solid state physics class. So what that means that instead of one band, now with this folding, you would get multiple bands displaced and overlap in the much smaller Brillouin zone. And when that happens, the different branches overlapping in the middle can form a new symmetrized state, which recover the same symmetry as the intralayer transition, and then can again very strongly hybridize with that intralayer transition and give us those split resonances. And we can also show that in this case, the different energy difference between the inter and the intralayer will follow a quadratic dependence based on the quadratic band. And interestingly, if you go to a twist angle where the Moire lattice, Brillouin zone, fits exactly into this original monolayer lattice. And what happens is that now this corners of the two monolayer, the blue corner and the red corner, that get displaced by a large amount in K-space, now actually becomes two equivalent points in this black hexagon or the Moire Brillouin zone. And that again makes them strongly coupled again, even though they have large displacement in K-space. And that's also what we have seen. Then that gives us a very strong evidence such a Moire lattice, superlattice, actually has formed. So I think it's already 7. Should I stop here or should I maybe go another 5-10 minutes?
Another 5 or 10 would perfectly be okay.
Okay, I'll try to finish maybe in 5 minutes. So what's nice about having a Moire lattice? One of the things that we are all interested in is how to get to ultra high energy efficiency, and also how to reduce the energy power and reduce the heat in order to go beyond the Moore's law, right? And one way to get there is to go to basically the smallest amount of energy you need to make an operation or to process a bit of information. And the smallest amount is basically a single excitation. And the way to get to a single excitation is to basically create what we call a quantum dot with a 3-dimensional confinement into a nanostructure so that a single electron, a single hole, or a single exciton will be confined. And when you put in another one, the energy will be shifted because the confinement is so strong, the interaction is so strong. So if you look at the same energy, you will never have more than one excitation. That gives you a way to access a single excitation. But those are nanometer scale structures, so they will couple very poorly to light because of mismatch in length scale. But what you can do is put it again in a cavity, such as this is example of photonic crystal cavity, to enhance the coupling. And this is a demonstration. You can use a single photon to switch to couple to the quantum dot to form basically a single photon switch. But that's a proof of concept demonstration. To use that for device turns out to be astronomically difficult because of the scalability problem. So these quantum dots are self-assembled or from either bottom up or top down, but always suffer from very large inhomogeneity, right? Even a nanometer fluctuation is huge for a nanometer scale structure. So it has been basically impossible to go beyond one dot or a couple dots. Now coming back to our Moire lattice, and there's my little cartoon to show how the Moire lattice changes when you change, for example, the twist angle. So what that gives us is now we have a lattice which has the natural length scale of that of a quantum dot of a few nanometers to a few tens nanometers. but they're naturally formed between two pristine crystal lattices. So in principle, you can get rid of any of the inhomogeneity that's intrinsic to any artificial quantum dot structures. So how do we know we have such a quantum dot confinement? And we come back to our polariton again. We put such a bilayer in the cavity, and we find they split, and they form strong coupling and split into different branches. Now we have two hybrid excitons, so we have three split polariton branches. And we can also compare that with what happens in the monolayer, which you have one exciton and split into two polariton branches. We can calculate the coupling strength. They add up because of the optical sum rule. They all work out. But what is interesting is if we look at how it changes with the excitation density. So here we are increasing the number of carriers we put into our system, number of electrons and holes we put into our system. So for the bilayer, you could see the energy shift of the polaritons shift symmetrically toward the exciton, which is very different from the monolayer. And we can go back to how the excitons behave. The red is for the bilayer with the Moire. The blue is for the monolayer without Moire. So I would just say that the blue agrees very well what we expect how a quantum well exciton will behave, or a two-dimensional exciton will behave. But the red agrees exactly what one would expect from a 0D exciton or fully confined exciton. So basically in the quantum well, you would have a shift and the broadening and a small saturation that's on the order of inverse of the Bohr radius of the exciton. But in the quantum dot, you would have no shift, you would have no broadening, and you would have a strong saturation on the length scale of the size of the quantum dot, and in this case, the period of our Moire lattice. And for the ones we already made, we can get the nonlinearity as a result, basically how much the energy shifts per electron hole pair we put into the system. And the red is for the Moire polaritons. Just to give a reference, the value of a nonlinearity here means that we need 0.02 excitations per site on average to produce a 1 electron volt shift. And 1 electron volt is about the homogeneous line width of those excitons. And that now if we take that many excitations and cover area that's diffraction limited or a reasonable sized 0D cavity structure, that corresponds to we need about 100 attojoule in order to switch that system. And we can reduce that further if we use a higher quality cavity to reduce the line width or to increase the Moire period and eventually reach the attojoule limit of information processing. So I think I will stop there, and I should mention this is a collaboration. The 2D material part is a part of a larger collaboration on the Moire program with many other colleagues with a field drive, and just to flash, that's how the actual setups look like, and that's where I do the fabrication, and these are the people who actually did the work. Okay.